So in today's class, we shall be starting with stochastic process, which is basically chapter 1 of CS2. So just to give you a background, this chapter is fundamental for CS2 as a lot of chapters later on will be drawing upon the various concepts as well as the various definitions of process, which we would be describing in this particular chapter. As for the link, CM2 paper also uses knowledge from this particular chapter itself. So some of the processes which we look here could be something which you might have encountered while, let's say, preparing for paper CS1. Also, just keep one more thing in mind. We would be going through the definitions of a number of processes, some of which will not be explained in detail in this particular class because those are separately discussed when a particular chapter dedicated towards it is being covered. So to begin with, first of all, let's define what exactly is a stochastic process. So do keep taking notes, all of you. So give the heading stochastic process, and then we shall start with the definition for same. A stochastic process is a model for time dependent random phenomenon. Full stop. It is a collection of random variables. Xt, this is the way you need to write. Xt, comma, one for each time, small t, one for each time, small t, in some set, SOME, in some set, capital J. Full stop. Next line. It is denoted by. Next line. The set of values that the random variable. Xt. This one again. Can take is called the state space of the process. Within brackets, capital S. That is, we denote the state space by capital S. Full stop. The values in the set J. Is called the time set of the process. Now we will look at exactly, this is just, let's say, the formal definition for a stochastic process. Now we will try to understand intuitively what exactly we are dealing with. I have a graph of it here. Let's look at this to begin with. On the x-axis, what we observe is basically time, and on the y-axis, what I plot is basically the temperature observed. Let's say this is the maximum temperature on each day. So you're looking at a graph. Now, if I want to model the highest or the maximum temperature observed each day, let's say forever, this can be, let's say, modeled using a stochastic process. Now, if you look at the definition, a stochastic process is nothing but a model for time-dependent random phenomenon. Here, what we're trying to observe is the maximum temperature. Here, time, the units which we are using is nothing but days. So, as the days passes, the first day comes. Once the first day is over, we would have observed the maximum temperature for the day, and we would have got a particular value for day one. Then we go to day two. Once day two has got over, we would be able to determine that what was the maximum temperature observed, and we'll have a particular value for day two as well, and so on. Similarly, we'll have for day three, four, five, so on. So this entire thing nothing but becomes a stochastic process. You can take any examples. For example, the closing price of a stock each day. This again could be modeled as a stochastic process. The amount of rainfall on each day, let's say the number of steps you have walked each day, the hours you have slept on each day, or each let's say hour, each week, each month. The time unit could be anything. It could be days, it could be weeks, it could be hour, it could be second, it could be anything. So initially in CS1, like the practical implication is in CS1, let's say we were at times interested with the number of claims or the amount of claims. If I talk about the number of claims, by definition, when I used to say X is the number of claims, we used to assume it is for a particular given period of time. If we do not specify the time limit, then it does not make sense, because we need to define that when I say that X follows the number of claims, I also need to complete it is the number of claims observed when, in a day, in a week, in a month, or in a particular year, say. So now there we were looking at a random variable where the time was fixed. Here we are extending how? By making time to be non-fixed in nature. So if I say that the claims process is a stochastic process, it makes sense. As time elapses, let's say claims, we would be experiencing claims which would be coming. Now I could, let's say, model the number of claims which we have received over the 2 years as a random variable, or the number of claims received in 3 years, 6 months, anything. Once we fixate a time, we get a random variable. In stochastic process, what we have is basically a collection of random variables. So say for example, to begin with, I could ask the question that for how many hours did you sleep on a particular day? Okay, let's say this is a random variable and I'm talking about a single day, let's say Monday. So say you slept for 7 hours. Fine. Now I might also be interested in next day how many hours you would be sleeping, and so on. So as you will see, the denotation, we are denoting it by how xt. So we can say that, taking my example, x1 will be 7. That is on first day. How many hours did we observe of sleep? 7 hours. Then on the second day, let's say we observed 8 hours. On the third day, let's say again 8 hours, so on. So is this thing clear? Now my sample space is basically the set of values which xt can take, and that is called basically the state space of the process. J is basically the times at which I am observing the process, and this denotes nothing but the time space of the process. Now, could you all tell me how many types of random variables we have seen? Two types of random variables, either discrete or continuous. Similarly, over here, be it the state space or be it the time set, it could either be, what to say, discrete or continuous. Just keep one thing in mind when I talk about time. Time in itself is always continuous. It depends how accurately we can measure. But when here I say that the number of slept in a day, in that case, I am defining time to be one single day, and in which case it will become nothing but discrete. If you're just measuring by seconds, then time becomes continuous. But here what I'm saying is I want the number of hours slept in a particular day. So this is how time becomes discrete, because my data point is coming, let's say, once every particular time interval only. So a lot of you might have questions, time to is always continuous and all. If I say that I am looking at the let's say uh, the temperature at 12 p.m. every day, then here my time becomes what? At least for my stochastic process, it becomes discrete in nature. Why? Because right now I checked at 12 p.m. That was the first data point. Next day again at 12 p.m. I will be checking for the temperature. If the question was if the question is observing temperature throughout time, Then you can observe at what, let's say 12 p.m. Now you could say that still, it is discrete, because what is the next possible time after 12 p.m.? You will say 12 p.m. 1 second. But that is only because you are used to using clocks where the minimum tick size is 1 second. You could go into milliseconds, nanoseconds, so on. Theoretically speaking, time is continuum in nature. But the point at which we are able to record data, that will ensure that time also behaves what somewhat in a discrete way, very theoretically speaking. So first of all,
x1, x2, x3, these are state space.
788 x1 denotes the value of the state space at time 1. So how you read xt is the value of the process at time t.
And 789 is the time space.
No, time space is 1, 2, 3. 788 is basically state space. X1 equal to 7. X1 is basically the value of the process at time 1. So the subscript that denotes the time at which you are observing the process, and xt in itself gives us the value, which here is 7, 8, and 8. Next, give the heading classification of stochastic process. Classification of stochastic process. So now, as I mentioned, the state space or the time set could either be continuous or discrete, and this will lead to basically 4 primary combinations: discrete, 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 continuous, continuous, discrete, and continuous, continuous. So right now, we can classify stochastic processes. We can classify stochastic process primarily into 4 different categories. Primarily into 4 different categories. Now in a tabular format, give the headings. First column header is state space. Second column header is time space. And third column header is example. So in the first column, you can write D, D, C, C in different lines. So D in first line, D in second line, C in third line, C in fourth line. Basically in this way. In the second column, you can write as DC, DC. So these are nothing but the 4 combinations. The first row, basically we are having a discrete state space and a discrete time set. Second one, we are having a discrete state space but a continuous time set, and similarly for the third and the fourth one. Now we will take a look at certain examples and we will see where do we encounter this process. Most of these we would be encountering in our paper CS2 only. Some of these processes would be encountered in paper CM2. So for the first one, the example is Markov chain. MARKOV, Markov chain. And we have a separate chapter, chapter number 2, devoted entirely to Markov chain. Second row, Markov jump process. So again, we have a chapter 4 and a chapter 5 devoted to basically Markov jump process. Give a common, right? Second example is Poisson process. We are talking about this combination only currently. Markov jump process and Poisson process. Note that these are just examples, not exhaustive in nature. Again, Poisson process is something which we already have studied in CS1. It will be there in CS2 as well, and it will be again there in paper CM2 as well. Next combination for the third one, write time series. Again, we would be encountering this in CS2 only. Chapter 13 and chapter 14 is completely devoted towards time series. And finally, for the last one, you can take the example as Brownian motion. Brownian motion. Some of you might have heard this term in school level as well in chemistry. Movement of a pollen grain when you drop it in water. So Brownian motion is something which is covered in paper CM2. So these are the combinations. Next, give the heading sample path. So now we would be defining or coming up with a lot of terms. We'll quickly note down the definitions for same, and then we would be solving a couple of questions which will sort of give you more clarity with respect to what each of the following terms imply. So for the sample part, the formal definition is this: a joint realization of the random variable, a joint realization of the random variable xt, xt, then write in this way for all t in J. This is the mathematical way to write for all t belonging to J. You can write mathematically in this way only. Is called the sample path of the process. Full stop. This is a function from J to S, JNS in capital. This is a function from J to S. Yes, both J and S capital. Now, what exactly do we mean by sample path? Take the literal meaning itself. Like for example, if I take this example only, the number of hours which we were observing to be slept on each day. Say I have observed for 3 days only. This entire thing is nothing but my sample path. By the term sample path, this is my sample and this is the path of the process. First it took the value 7, then it took the value 8, and then again it took the value 8. So is this clear? The formal definition is a joint realization of random variables, so on. Logically, what is sample path? Basically, whatever past values you have observed for the process at all possible points of time, that is nothing but my sample path of the process. It is also mentioned that it is a function from G to S. So if you will remember, once we define a function, there is something called a domain and there is something called a range. Domain is the set of values for which the function is defined. Range is the set of possible values which the function can take. So here if you look at time 1, 2, 3, this becomes my what? Let's say domain over here. Because fundamentally it is the time which is leading to a change in the value of the process. Only when time changes will we be able to observe the value of the process. So 1, 2, 3 is nothing but J. This you could visualize it as what? As the domain of the function. 7, 8, 8 is nothing but basically becomes, let's say, the range. So that is why it's written that this is a function from J to S. Mathematically, within brackets, write this J to S. So is the definition of sample path clear? Again, mathematically, it's given as joint realization of random variable. Again, at a very simple level, nothing. You just need to look at the value of the processes till the observed time, and that is nothing but the sample path. The data which you are collecting, right? The data as well as the points at which you are observing the particular data. So this data in its entirety is called sample path. If I just write, let's say 7, 8, 8, this would be the sample path. You need the time as well as the value at that particular point of time. Others who are attending the live online session, is this clear? Let me know through chat box. Then I'll proceed to the next one. Okay. So next, give the heading stationarity. Next, give the heading stationarity. Spelling is this. Sorry, okay. Before moving to stationarity, we saw 4 possible combinations. One was discrete, discrete, then discrete, continuous, continuous, discrete, continuous, continuous. There is another type. So give that heading one. Mixed type process. Mixed type process or processes of mixed type. Either way you could do. So what happens in mixed type is certain events when we're looking at will operate in continuous time, while certain events are going to occur only on discrete points of time. So let's say I am looking at what the process which I am looking at is the number of I am looking at the number of students in the classroom. Okay. Now, just at a very simplistic level, let's say that the classes goes on for 12 hours. The students can join at any point of time. They can join, let's say, at 9 a.m., 10 a.m., 2 p.m., 4 p.m. at any point of time. But students can leave only at integer points of time. That is only at either 9 a.m. or 10 a.m. or 11 a.m. or 12 a.m., 12 p.m., 1 p.m., so on. They cannot leave midway. Okay. So now when you look at this process, my observation is what the number of students in classroom. This is composed of two processes. One, number of students entering the classroom. Second, number of students leaving the classroom. The number of students entering the classroom, as per my example, is operates in continuous time because a student can join at any point of time. But the number of students leaving the classroom is occurring only at discrete points of time because that is the way I've defined it. So this will become nothing but an example of a process of a mixed type. So if we quickly go through this, just because a stochastic process operates in continuous time does not mean that it cannot also change value at predetermined discrete instants. Such processes are said to be of mixed type. As an example, on this we look at a more practical example from the point of view of, let's say, insurance company or a pension scheme. Consider a pension scheme in which members have the option to retire on any birthday between age 60 and 65. The number of people electing to take retirement at each year of age between 62 and 65 cannot be predicted exactly, nor can the time and number of deaths among active members. Hence, the number of contributors to the pension scheme can be modeled as a stochastic process of mixed type with state space s equal to 1, 2, 3, so on, and time interval is 0 to infinite. Decrements of random amounts will occur at fixed dates due to retirement as well as at random dates due to death. So here when I take a look at the decrements, or let's say the number of people dying, people can die at any point of time. So this is operating in continuous time. But the people who are retiring will occur only at discrete points of time because here we are saying that the people who will retire will be retiring on their birthdays, either at age 60 or 61 or 62 or 63 or 64 or 65. So this process is a combination of mixture of two processes, a stochastic process modeling the number of deaths, which has a discrete state space and a continuous time set, a stochastic process modeling the number of retirements, which has a discrete state space and a discrete time set. So is this definition of process of mixed type clear? Generally, when we look at processes of mixed type, the process which we're looking at can be subdivided into, let's say, two or more than two processes. One of which, let's say, will be having continuous time and the other would be having, let's say, discrete time. Now, before we move forward to, let's say, stationarity, come up with examples for each type. That is, think of any practical example. Let's say from the point of view of a retailer, a normal retailer shop, give me an example where the state space is discrete as well as the time set is discrete. Consider a retail shopkeeper taking any examples which he or she might be involved in. Give an example of a process which will have a discrete state space and a discrete time set.
Number of books is sold.
Number of books he sells
In day 1, 3 books.
in each day. So one of you has given the example, the number of books being sold each day. Number of books being sold will be what? 0, 1, 2, 3, 4, so on. It could be negative if, let's say, there is somebody who is coming and returning the book, if that is allowed. So my state space becomes what? Discrete. Again, I hope that you all do understand the difference between discrete and continuous. If not, there is a particular lecture available on our YouTube channel for the topic random variable. You could just revise it just to be a bit more clear with respect to the difference between a discrete random variable and a continuous random variable. So this was one example. Again, it is very important to mention the number of books sold each day. Just saying number of books sold does not make sense, because number of big books sold in what time, that nobody has mentioned. So it is required you mention the time interval as well. Another example is number of orders made for bulk products each day or each week. Fine, perfect. This is also correct. The time at which the shop is closing, then here it theoretically it won't be discrete time. Rather, time will be discrete each day. Here my time is each day. Then you're looking at the time at which closes. That will become my state space. So that could be any point of time. If you mention rounded off to the nearest second, then it can become discrete. If you just say the time at which the shop closes each day, so this has a discrete time, but its state space is continuous in nature. Then another example could be the total sales made each hour. This will also have a discrete state space and a discrete time set. Note that when I say total sales, again we're operating what? If we're talking in terms of rupee, the lowest denomination will be multiple of 1 paisa. If we're talking, let's say, in dollars, then the lowest possibility will be 1 cent, so on. So again, this becomes discrete. Although, just keep this in mind, at a very practical level, if I talk about a large retailer, where say on hourly basis it is making total sales of lakhs or crores of rupees, for example, in that case, let's say one possible value is 1 crore of sales. What is the next possibility? 1 crore, 1 paisa. These, with respect to the magnitude and value, the tick size here is what? 1 paisa. The increments or the difference in the two possible values which we can observe. 1 paisa compared to 1 crore is very small. So for practical purposes, we can assume here that the amount of sales is continuous in nature. Like a lot of times, even in practical scenarios, when we want to model the amount of claims, insurance companies use the generally what? Continuous distributions to model these. A natural question you will have is that the claim amount should be what? Generally rounded off to the nearest integer. So technically it should be what? Discrete. But we are talking about claims of what size? Could be in thousands, lakh, crores, so on. So given this, typical values which the claims state and the small difference in the values, we can approximate it to what? To be continuous in nature. So let's take about this. Let me take two cases. One random variable x. This can take the possible values 0 0.01, 0 0.02, 0 0.03, so on. There's another random variable y, let's say, which can take the values 100, 100.01, 100.02, so on. Both of them are having a tick size of 0.01. When I say tick size, what I mean is basically the step size from one value to another possible value. Here, I cannot assume this to be continuous because the possible values which x can take and the tick size are very much similar in magnitude. Possible values are what? 0 0.01, 0 0.02. Let's say I say this ends till 1.00. So here if you will see that the tick size is, let's say, 0.01 and the typical value lies between 0 and 1 only. So here both the magnitude are similar in nature. So this you cannot approximate to be continuous. Even if you do, it will be a very bad approximation. Here in this case, the typical values is what? 100 or so. Now the tick size over here is 0.01, which is a very small magnitude relative to 100. So here you might assume this to be what? Continuous in nature. So this is just mathematical way to see when it would make sense, or how good would your continuous approximation be to any discrete thing. Note that whenever we try to measure something, inherently when we measure thing, we do it till a particular decimal place only, or maybe to the nearest integer. So automatically, these things become what? Discrete in nature. Just for one example, if I want to measure the weight, whenever you measure these things, if you're measuring weight, this will actually have what? Continuous values. You can measure till what? 57.23487775 kilograms, so on. If I say quote answers till the nearest kilograms or till maximum one decimal place, in that case it will become what? Discrete in nature. So whenever you measure these things, these are generally what? Continuous in nature. Just because we quote our answers till a certain decimal place, that is why it looks at it is what? Discrete in nature. Similarly, temperature, it could be what? 26.6345 degrees Celsius, so on. Number of students, number of books, these are what? These inherently will be discrete in nature. One book, two book. Again, assuming if you tear off the book, there is nothing called a 1.5 book or so. Number of children, then anything else. Number of claims, these are always what? Discrete in nature. So let's say, just hypothetically, if say we say the students to set up very small insurance companies, okay, where the claim amounts are typically of 0.01, 0.02, 0.03, so on. In this case, if you approximate your claims to be continuous in nature, that will be a bad approximation. Whether in practice it is done or not is a separate thing. Theoretically speaking, it will be a bad approximation. But let's say if the claim amounts are typically of size 100, then you can approximate this to be what? Continuous. So this was the underlying thing which I was mentioning. Again, few of you have come up with more examples. The minutes spent in the shop each day. This again becomes an example which has a discrete state space and a discrete time set. Then number of payments made through credit card in a day. Again, yes, this is also correct example. Next, give an example wherein we are having a discrete state space and a continuous time set. See, one thing, a very easy way of doing that is we took an example of number of books sold each day. Now, if I say number of books sold till time t, this will become a continuous time space, because time t can take any continuous value. So this is one very easy way. Whichever example you take of discrete, just modify that each day, each unit of time to till time t itself. Apart from that, if I say the temperature at each point of time, then again this will have a discrete state space, assuming that I'm rounding off temperature till, let's say, maximum one decimal point, and my time here again can be taken is what? Basically continuous in nature. So next one, third one, continuous state space, discrete time set. Give an example of this from the point of view of a retail shopkeeper. Number of customers, those state space become discrete. Time spent in shop each day, again makes sense. The time spent in shop each day. So if I want to try to measure time, this will be what? Continuous in nature. So my state space becomes continuous and I'm measuring it each day. So my time set is nothing but discrete. Again, as I also mentioned, one question. Let's say if this retailer is a big retailer, okay, then I can say the total sales made, the total amount of sales made each day. If the amount of sales are, let's say, in the tune of, let's say, lakhs or crores of rupees, I can assume that these are nothing but continuous in nature. Clear? Again, when you try to look at this on the state space, most of the time it will look discrete only, but just keep this thing in mind. The example which I give, if the tick size is relatively small compared to the typical values which the random variable is expected to take, then you can approximate to be what? Continuous in nature. Final one. You can start with one example, like whenever these let's say retailer is there, or let me take another example. Let me talk about insurance company. First one would be number of claims each day. Next one would be number of claims till time t. Third one will be amount of claims each day. The last combination of continuous will be amount of claims till time t. Here, this is for an insurance company. Again, for a shop retailer, we started with first thing, number of sales each day. number of sales till time t, amount of sales each day, amount of sales till time t. A lot of times in the question they will say give 4 different examples. So there the first 2 examples are related. Number of books sold each day, number of books sold till time t, these will not be counted as, let's say, 2 different examples. So you need to come up with something else. You could say that uh, what was it? Number of 100 rupees received till time t. This will have a discrete state space and a continuous time set. So moving forward, stationarity where we were. So take down this definition. I'm not dictating, but do take down this in the form of notes in a notebook. Okay. Sample part I have described. Fine. Now in stationarity, just keep in mind, we have 2 types of stationarity. One is called strictly or strict stationarity. The next one is weakly stationarity. What do we mean by strict and weak? We are gonna see. So first write the definition of strict stationarity. It's there here highlighted in bold. So do take this down. K plus Tn, n is in subscript, and K plus Tnr is also in subscript. So again, in simple terms, a process is said to be strictly stationary if the statistical properties of the process remains unchanged over time. Next, give the definition of weakly stationary. Again, is the concept of strict stationarity clear? What it means that the statistical properties of the process should remain unchanged as time elapses. So whether we are looking at the distribution of say x1 or x2 or x10 or x20 so on, the statistical properties of all of these should remain the same. Then the process is said to be strictly stationary in nature. Again, the more formal way of saying that is the way they have described it. In examination, if they ask you the definition of strict stationarity, you'll need to mention this entire thing. Just saying that it means that the statistical properties of the process remains unchanged will not be the correct way to define it. That is the correct way to understand it, but not the correct way to define it. So next, give the heading weakly stationarity. A process is said to be weakly stationary. A process is said to be weakly stationary. First point. Expectation xt is constant for all t. And then the second point, covariance xt comma xt plus k depends only on the lag k. Second point. Now see, the practical reason is that if we try to model any stochastic process, let's say for example, I wanted to model the temperature for the past 100 years. Now, obviously, the temperature or the climatic conditions at a particular place, would have changed significantly over the past 100 years. So, strict stationarity is a very rigid condition. If you would try to observe a process, then most of the physical processes will never be strictly stationary in nature. So that is why we come up with what weakly stationary, wherein we are just looking at the first two moments of the process. Expectation is the first one, so it should be constant for all t. Second, covariance should only depend on lag. Now, what do we mean by lag over here? So, covariance of, let's say, x2 comma x6, the lag is nothing but the difference in time, which here is nothing but 4. This should be equal to combinations of all covariances which has a lag of 4. That is, it should be equal to covariance of, let's say, x3 comma x7, or covariance of x6 comma x10, so on. So wherever lag is 4, all those combinations should have the same value. Note that covariance of, let's say, x1 comma x3, this has a lag of 2. So this will be, this could be different of this one, but this should be equal to, let's say, covariance x4 comma x6, or let's say covariance x7 comma x9. More generally, this should be equal to covariance xt comma xt plus 2. So in a more general format, we have summarized in this way: covariance xt comma xt plus k only depends on the lag k, it does not depend on the time t. Note that this also has another implication, that variance of the process is constant. Remember that variance xt is nothing but covariance of xt comma xt. So if we'll put k as 0 over here, then covariance xt comma xt becomes nothing but variance xt in itself. So this comes under my weak stationarity. Next, give the heading increment. Increment. Rather, increments. An increment of a process is the amount by which its value changes over a period of time. An increment of a process is the amount by which its value changes over a period of time. Example, xt plus u minus xt, where u is greater than 0. Now do keep in mind the way we would be defining an increment is final value minus initial value. If you will see that they have written u is greater than 0, it means that t plus u will be greater than t. So it is actually what? after value minus before value, or you could say it to be final value minus before value. So this would be qualifying as a definition of an increment. Let's say x6 minus x5 or x7 minus x4. But if I write x2 minus x3, this does not qualify as an increment. It should be after time minus the prior time or the previous time. So now often at times the process in itself could be very difficult to model. But if we look at the increments of the process, then those might have more simpler statistical properties compared to the original process itself. So this was under increments. Next, independent increments. Independent increments. So take this down. A process xt is said to have independent increments. A process xt is said to have independent increments if for all t and every u greater than 0, the increment xt plus u minus xt is independent of all the past of the process. So in simplicity, what independent increments says that if a process has this particular property, then the change in the value of the process will be independent of its entire past. So you can take this example, say x6 minus x3. This shall be independent of x3, x2, x1. If I have x0, x minus 1, anything, what, just keep in mind everywhere, I'm taking the time space to be 3 to 1, so on. It could be 3, 2.5 to 1.5, it could be anything. So my point is that x6 minus x3 is independent of what? Anything up till time 3. So if I draw a timeline, let's say this is t plus u and this is t. And I have the increment xt plus u minus xt. So this is independent of what? Entire thing on and before time t. And note that t is also included. x6 minus x3 is independent of x3 as well. If you will take a look at the definition, s is less than equal to t as well. It means that xt plus u minus xt is independent of xt as well. In my example, what I'm trying to simply say is x6 minus x3 is independent of x3 as well. So how we use this is, let's say here xt has independent increments. What it implies is, if I try to find covariance of xt plus u minus xt comma xt, remember that if two things are independent, then their covariance is 0. I am saying the process xt has independent increments. It means that xt plus u minus xt will be independent of xt as well. So this covariance should nothing but be 0. Also keep in mind, covariance of two random variables being 0 does not necessarily imply that they both are independent. It only implies that they are linearly independent. There could be some form of other non-linear relationship too. So you can just take them down. X6 minus x3 is independent of x3 comma x2, so on. xt plus u minus xt is independent of xs. S can take any value between 0 to t. So even if it takes t, so next give the heading Markov property. So under Markov property, take down this. If the future development of a process, if the future development of a process can be predicted, can be predicted from its present state alone, from its present state alone, without any reference to its past history, without any reference to its past history, comma, then the process possesses Markov property. Mathematically, take this section till here basically. That is starting from here. Yes. Just replace one thing instead of writing xt belongs to the set capital A, just write it as xt equal to A over here, xt equal to A small a, and here as well make that adjustment. This particular part, just write xt equal to A only, small a, yeah. Rest all remains the same. And while taking this line, this will be for all times and all states x1, x2, xn, comma a and xns. Just need to write till here. Just write us add a small a as well. So see, basically over here, what I've assumed is that the state space is discrete as well as the time set is discrete in nature. There are similar ways of defining Markov process depending on the combination of state space as well as the time set. So the one which you will actually see right now on the screen, this is for a continuous state space and a discrete time set. That is why they had written xt belongs to the set A. So now know what exactly do we mean by Markov property? It simply means that if by using information available till today, if I can predict the future, then I would say that the process is Markov in nature. So say for example, hmm, uh, let's talk about the progress made in school itself. There is one final examination which a student needs to sit for. If he or she clears that examination, he or she will be promoted to the next class. Now, in that particular examination, if a student A passes, now using that information alone, I can say that what the student would be getting promoted to B. So I can predict the future just knowing the present exam only. Whatever the marks a student scores on that paper, basis that we can predict whether the student will be getting promoted or not. There is no requirement to go to the past itself, right? In certain cases, it might get required. So just let me take an example. There's a particular school, take care, a slightly corrupt school, which allows students to get promoted to higher class even if they fail their examinations. But it only allows students once to pay money and get promoted in its entire 12 year of schooling. There are two sections. One is section A, one is section B. Okay. Uh, Section A basically has those students which have never paid money to get promotion. Section B has those students which have paid money to get promotion at any point of time. Now let's talk about a student who is in class 5. If I now this student needs to sit for an examination, if he or she clears the exam, she would be going to or he or she would be going to class 6. But can you tell me what will happen if he or she fails the examination? Why? ठीक है. So see, again I'll repeat my example. I want to model the movement of a student's progress through different classes. Currently, the student of concern is in class 5. Now to question, whether this, what will happen next year to this particular student. Post the results of exam. If he or she is clearing the exam, student will go from class 5 to class 6. If not clearing the exam, then we need to see whether the student has paid money earlier or not. If the student has paid money earlier, then there is no provision to pay again. The student will remain in class 5 only. If the student that has not paid money earlier, then the student has an option. If it is willing to pay, it will go to class 6. If it is not willing to pay, it will remain in class 5 only. Point is just on the basis of the information of that examination, I cannot determine the future. I need some information regarding the past as well. So this process will not possess Markov property. Originally, when I just say about 5, now if I say you a student from YV appeared for the examination. Now tell me whether can we determine what will happen. Yes, if the student clears the exam, he or she will be going to class 6. If the student does not clear the exam, then if he or she pays money, goes to class 6. If he or she does not pay money, he or she goes to section 5B, because A has ones who have never paid. Now, if I talk about a student who is in 5B, for that it is even simpler. If the student passes, goes to class 6. If the student fails, remains in 5B only. So now here what I said was, this will help you in chapter 2 onwards. Initially, if I was modeling only through, by making the state space as class 5, class 6, so on, this process will not possess Markov property because we cannot track the movement from 5 to 6 without knowing what happened earlier. But the moment I, bring in states like 5A, 5B, 6A, 6B, so on, in this case, automatically 5A conveys the information, 5B conveys information, and now this entire process becomes what? Markov in nature. The moment I say 5A, 5B, that is having additional detail with itself as well. The moment I know it's, you're in section 5A, I automatically know that you have never paid money in past. So now it doesn't even matter what happens in 4, 3 or 2 because 5A automatically is giving you that information. So this is again something which will help you a lot in chapter number 2 when you have to create models. So initially you could start with making some state spaces, Okay, then you need to check whether that is satisfying Markov property or not, and if it is not satisfying, then you'll have to define certain additional states so that you can model it according to a Markov, so that it has Markov property. Now, why Markov property is so important is because only using the current information you can predict about future. You do not require any information regarding the past. And this makes the modeling part, or let's say the prediction part, a lot more easier. So that is why even in real life, we want the models to be what Markov in nature, because they're just using the present set of information, you can determine what about future itself. Also keep in mind, if even the present information is not required to determine what happens in future, then that is also nothing but possesses Markov property. So more, in a better way, Markov property is satisfied when we are able to determine the future by having knowledge of maximum of present only. Even if we do not have knowledge of present, still if we can predict future, it possesses Markov property. At the most, the knowledge which we require is of present only to determine future. So this is regarding Markov property. Again, just keep in mind, if in the question, some explicit details has been given, whether the state space is continuous or discrete, you need to modify your formula accordingly. So the one which you have written down, that is applicable in case of a discrete state space. Here, this is applicable in case of a continuous state space. And now let us try to make sense. If I want the probability of xt taking the value a, the one which we have written in the notes, given that at time s1 it had value x1, s2, sn, and s so on, where small s is the last time which was observed. This is nothing but equal to the probability of xt taking the value a given xs is equal to x. So Markov basically implies one-step dependency. To know what will happen at time t, the maximum knowledge which we need is till time t minus 1. Here, time s is the last point of time where I had the value, and t is the next point of time. So to determine what happens in t, we do not need values at time s1, s2, sn. All we need is information regarding the value of process at time s. If you will see on RHS, we are just taking which part xs is equal to x. All we are concerned is which part time s only. The other times sn, s2, s1, all these are not required. Just time before x. Yes, if you will see over here, now s1 less than s2, s2 less than s3, sn is less than s, s is less than t. So the last time before t at which we knew the value of the process was nothing but time s. Another way to understand is Markov property means one-step dependency. To estimate what happens in t, all you need is what till t minus 1. Again, if the time step is an increment of 2, then to estimate what happens in t, my time step will become what? T minus 2. Just think at whichever points of time you're observing the process. The next time you want to predict it, all you need is current value. So this becomes my definition of Markov property. Next,
in time is so like the next time is t at time t1. So with the if I am predicting the future to time t1, will that be Markov's property?
no, that is two-step dependency. Markov means if I know about s, I can predict about t. Whether I can predict about next time after t or not, it depends. If we can find, if we cannot, still it does not hamper Markov property. Markov property is for one step only. If you not using the knowledge till time 1, if you can predict what will happen in time 2, then that is said to be possessing Markov's property. Next, right, just below this only, a process which has independent increments, possesses the Markov property. The other way around is not true though. If a process has independent increments, it will definitely have or possess Markov property, but a process which possesses Markov property does not necessarily need to have independent increments. We'll see a mathematical proof of this as well. Let us take a look at that right now only. So give the heading proof of the above property. Proof of the above property. Again, replace everything belonging to capital A with xt equal to A. So take this down, then I'll explain. Or instead, before taking down, let's try to understand what we're trying to do over here. We are starting with this, that is the LHS, probability xt equal to A, given the different values at different points of time. Now what we're looking is to use the property of what? Independent increments. So I am doing what? Subtracting excess and adding plus x. Because at excess, the value is nothing but small x only. So it's nothing but basically adding and subtracting the same quantity in the next step. Xs is nothing but x only. So I'm adding small x and I'm subtracting capital X's. Again, both are the same thing, just writing it different way because I'll need to use it differently. Now, next step, what I will do is this small x I can take on, let me write it over here. Probability xt equal to A, given lot of things x1 equal to x1, so on xs equal to x. Next step, what I write is probability xt minus xs is equal to, let's say, A minus xs given. Again, the same thing. Next step, what I write is xt minus xs is equal to A minus x given the above things. Just written one more step in between. I have subtracted xs on both the sides. Here, what I have replaced xs is with nothing, it is realized value, which is small x. Now, xt minus xs is nothing but an increment. We know that the process is having independent increments right now. So if this process has independent increments, then xt minus xs will be independent of its entire past. It will be independent of even xs. So this can directly be written as what? Probability xt minus xs equal to A minus x. Because xt minus xs is independent of its entire past. Now this is not directly coming in the format we need, right? Now my point is, if I tell you that A and B are independent events, then can I write probability A as nothing but probability A given B? If A and B are independent events, then can I write probability A as nothing but probability A given B? Yes, I can do that. So I know that xt minus xs is independent of xs. Still, I can write in this way as well. And only reason of doing that is to bring it in a format which is, comparable. Again, I'll go from here to here. What we're doing is xt minus xs is independent of its entire past. That is, it is independent of xs1, xs2, xsn, and even xs. But I'm just writing till xs. You can, and then in the next step, xs is nothing but x only. So again, this x and x gets cancelled out, and we're left with probability xt equal to A given xs is equal to small x.
So आप इतना equal to
किसको?
A.
Small a, any value, could be anything. So here the main step is, first of all, I am subtracting x's. In the next step, I am replacing the value of capital X's with small x only on one side. You might ask, why not on the both the sides? Because we need a result in a particular format. That is why we are going with this following methodology. And in the next one, although xt minus xs is independent of everything, just to bring it in a format in the way which we have defined Markov property, we can just add this excess as well. And this is using the fact that probability A is nothing but can be written as probability A given B, given that A and B are independent. And then again in the next step, I am replacing capital X's and small x. So this is the mathematical proof. Again, just see if all of you are clear. Next, give the heading filtration. Filtration. Again, it's not referred to as the purification of water, separate meaning over here. So write down filtration gives us information. Filtration gives us information about the past history of the process. About the past history of the process. So why do we use this is, say when we are having discrete points of time, okay, and if I tell you, right, give me the entire past history, you can note down at the first point of time this was the value, at second point of time this much value, so on, because there will be what, exhaustive numbers, right? If there is continuous time, in that case, if I tell you that at first point of time, say if I want to observe the temperature on a regular basis, at 12 p.m., let's say the temperature was 25 degrees Celsius. Can you tell me what will be the next time after 12 p.m.? We don't know. You could say 12 p.m. 1 second, I could say 1 millisecond, nanosecond, so on. And now there are going to be infinite values. So we cannot write it down. So the moment continuous time comes, just for notation purpose, we come up with this definition of filtration. So how we define is FT. This basically filtration. This is basically nothing but giving us the value of the entire process, the past history of the process rather. So instead of writing x1 is this value, x2, x3, so on, ft means I have the value of xs for all values of s between 0 to t, including both 0 and t. So filtration is nothing but giving us information about the past history of process. Again, the mathematical definition of this is slightly more complex. For understanding wise, this is what filtration is doing. So if you want to, let's say, talk about Markov's property, right? This is the way I could write probability xt equal to a given fs is nothing but probability xt equal to a given xs. Fs means what? Given what? The values at all points of time from time 0 to time s. All we need is the value at time S only. Obviously, given that S is less than T. So this is another way to write Markov if we are operating in a continuous time. So you can take this down, add it up. This is the way to express Markov property in case of discrete space and a continuous time set. Next, common examples of stochastic process. Common examples of stochastic process. First one, white noise. White noise. WHITE, white noise. NOISE. Second, counting process. Third, Poisson process. Fourth, compound Poisson process. Fifth, time series. Six, general random walk. General random walk. Seventh, simple random walk. So now take this question. Consider the process. Consider the process xt is equal to xt minus 1 plus yt. Next, where yt is equal to plus 1 or minus 1 with respective probabilities p and 1 minus p. Part 1. Calculate question 1, question 2. Third one, write down the joint distribution. Write down the joint distribution of x1 and x3. Write down the joint distribution of x1 and x3 given x0 is equal to 100. Given x0 is equal to 100. Part 4. Show that, check whether the process xt stationary or not. Acha, note that in examination point of view, whenever they ask whether a process is stationary or not, we basically have to check whether it is weakly stationary or not. मतलब mean निकालना expectation xt and covariance, and we need to check whether it is stationary or not. Take the next question. Xt is equal to xt minus 1 plus it, where it can take the value plus 1 or minus 1, and probabilities what I've written is e to the power minus mod xt minus 1. T minus 1 is in subscript actually, and the second probability is 1 minus this term. Check whether the process has part 1 independent increments, part 2 Markov property. Check के साथ ना check and explain whether the process has part 1 independent increments, part 2 Markov property. Before I attempt this question, the 5-6 common processes which I mentioned, the definition of these are given in the material itself. Time series is something we would be looking in more detail when we do that chapter. Poisson process, there is a separate lecture for that. Compound Poisson process, we would be dealing when we cover chapter number 19 and 20, that is for risk models. So for the time being, you can just take a look at what is given in material. Initially, you might not be able to fully appreciate what they're mentioning. Once you're done with these chapters, you come back and go through chapter 1, you would be able to understand all these different processes. So take 15 to 20 minutes or so and attempt these 2 questions. Hope that you have given it a shot. Once looking at the recording, please try for some time, 20 minutes, 30 minutes or so, and then you can again come back and watch this part. So the approach shall be this. For the first question, start from the first principle itself. X1 will be nothing but X0 plus Y1, which becomes 100 plus Y1. Now y1 can either take the values plus 1 or minus 1. So my distribution of x1 will be 101, 99 with probabilities p and 1 minus p respectively. Now similarly x2 is nothing but x1 plus y2. Right. So now x1 can either take value 101 or 99. If it takes the value 101, then x2 will either take the value 102 or 100. If x1 is taking the value 99, in that case x2 will either take the value 100 or 98. So basically you can draw a tree diagram of this format where 100 is the starting point. This is x0. This is 100. Next 101 or 99, 102 or 100, 100 or 98, 103, 101, 99, 97, 104, 102, 100, 98, 96. And this is x0, this is x1, this is x2, this is x3, this is x4. All the up step will be having probability of p, all the down step will be having probability of 1 minus p. Now, for the first part, before getting into technicality, you will clearly see that x4 doesn't take the value 103. Okay, so the probability will be nothing but what? 0. We need to find the probability that x2 is 100 and x4 is 103 given x0 is 100. We clearly see from diagram it's coming out to be 0. That is one way. Another way, had you been able to interpret mentally only, this is the steps, the way it's gonna work for the values. Then if you will see x1, x3, x5, all these are odd numbered values. These will only have odd values because we're starting from 100 at time 0. So at time 1, it will be either 101 or 99. At time 3, similarly, you will see 97, 99, 101, 103, so on. So all the odd numbered times will have only odd values, and the even numbered times will only can take even values. So clearly x4 equal to 103 is not possible, and therefore we have shown that the probability is 0. So instead of drawing this tree diagram, you could have solved the first part as it is. For the second part, where we want x2 as 100 and x4 as 102. So we want x2 as 100. Now, this particular probability which we are looking for, this can be broken down into this way. This is nothing but probability x2 equal to 100 comma x4 equal to 102. This comma here is working in the form of and. Generally you can relate comma as or, but here it's working in the form of and. X2 should be 100 and x4 should be 102. So probability x2 equal to 100 given x0 is 100, and then we want x4 to be 102 given that x2 is 100 and x0 is 100, right? So now this probability x2 equal to 100 given x0 equal to 100, there are two ways: 100, 101, 100, or 100, 99, 100. The probability of this is p into 1 minus p. This one is p, this one is 1 minus p, and here this will be 1 minus p and p. So this will be 1 minus p into p. We will be adding both of them because these are two different ways in which we can start from 100 and reach 100. So this probability will be nothing but what? 2p 1 minus p. Similarly, x0 is 100, we need x2 also as 100, okay? And we want x4 as 102. So the possibility of this is what? 100 to 101 to 102, or 100, or is there any other way? No. If x2 is 100, there is only one way for x4 to be 102, which is this path. And the probability of this is nothing but p square. So into p square. Note that this 100 is of time x2. From x0 to x2 we have already captured here. This is basically probability what? X2 is 100, we need to start from that, and x4 is what? 102. So this becomes my probability p square. So the final answer
100 minus 100 minus 100.
p into p. 100 to 101 is p, 101 to 102 is also p. So p square.
P into 1 minus 300.
From 100 to 101, this will happen when yt takes the value 1. So probability p. 101 to 100, this will happen when yt takes the value minus 1. Probability of that is 1 minus p. So p into 1 minus p. Similarly here, first from 100 to 99, yt should take value minus 1. So 1 minus p is the probability of that. And then from 99 to 100, yt should take the value 1. Probability of that is p. So this becomes my answer, 2p cube into 1 minus p. For the next part,
Tree diagram.
for the next part, we need a joint distribution, so the table will look something of this form. X1 can take the value either 99 or 101, and X3 can take the value 97, 99, 101, 103. So now this probability, this element is nothing but probability x1 equal to 99 and x3 equal to 97. If you will see, this is only possible if we keep moving down in all three times, probability of which will be nothing but 1 minus p whole cube. If x1 is 99, x3 cannot be 103. We are starting from 100, then we are moving to 99. Maximum which x1 can be is 101 only. So this probability now, given x1 is 99, sorry, x1 is 99 and x3 is 99. If you will see, you know how, acha nahi, chalo. Let's do it this way only. 100, 99, 100, 99. This is one way. Next way is 100, 99, 98, 99. This is the way in which x1 will be 99 and x3 will be 99. Probability this 1 minus p, 1 minus p. So this becomes what? P into 1 minus p whole square. Similarly, here also 100 to 99, 99 to 98 is 1 minus p whole square into p. So what I'm left with? 2p, 1 minus p whole square. 101. The only possibility is 1 minus p into p into p. And if you will add all of these up, this will be nothing but coming out to be 1 minus p. You know, you can write directly also how, if you would remember, adding all these particular, let's say different columns will give nothing but the marginal distribution of x1 equal to 99, which is nothing but 1 minus p only. So you can mathematically expand this and add up. Logically, this is how you can get the result. Now let's try this one. X1 is 101, x3 97, 0. If x1 is 101, x3 can be what? Maximum or minimum 99 only. X1 is 101, x3 is 99. This will be P. Achha nahi. First, let us go for principle wise. 100, 101, 100, 99. This is the only way. So this will be P into 1 minus P whole square. Then next one, 100, 101, 102, 101, 100, 101, 100, 101. So here this will be 2p square, 1 minus p, and 103, this will be p cube. If you will add all these up, this will come out to be nothing but p only. And if we'll add the columns, as in the different rows of each column, 1 minus p whole cube and if we closely look at the probabilities, these are nothing but coming out to be binomial expansions. 97, 1 minus p whole cube, 99, 3p 1 minus p whole square, 101, 3p square into 1 minus p, 103 p cube. In case of x1, p1 minus p. Had you taken x2, that would have been p square, 2p1 minus p, 1 minus p whole square. So this becomes my joint distribution of x1 and x3. Next is to check whether the process is stationary or not. So we can directly see that the distribution is only changing. X1 can take 99 or 101. X1 can take the value 99 or 101, whereas x2 takes different values. So clearly distribution of what x1 and x2 are different. Therefore, the process is not stationary. You could have calculated expectation xt as well, covariance as well, but here clearly you see that the distribution is only changing. Directly you can conclude that the process is not stationary.
So we need to show it in the exam.
You can either verbally explain when this is visible, or you can calculate expectation xt and you will show that it is not coming out to be constant. So here if you just take, you can, let's say, calculate expectation x1 and expectation x2, and these won't be the same in all cases, and it is always easier disproving. The moment you show that expectation xt is not constant, this condition is not satisfied, therefore process is not stationary. If we have to prove something, then you need to satisfy all the conditions. So those type of questions will also be there when you have to prove it. So you need to find expectation xt, and then you will show the expectation xt is coming out to be what, constant in nature, and similarly you need to find covariance. Again, this is something it would be, we would be doing that in time series as well, a lot of them. So this was the first question. Now for the second question. Again, similar in structure to the first one, just that the probabilities of yt were constant previously. In this case, the probabilities are dependent on the past value of the process. So first part is to check whether it has, let's say, Markov property or not. That was the first part, and independent increments. So xt was xt minus 1 plus it. So my increment will be nothing but what, xt minus 1. This becomes my increment, natural increment directly coming, and this is nothing but what, it. So this is the increment. Effectively, it is nothing but increment. It takes what values, +1 or -1 only. ठीक है, and अच्छा, it takes +1 or -1. Probabilities are dependent on what, xt minus 1 only. So can I say that xt minus 1, the value of this is either +1 or -1, and the probabilities of this will be what, e to the power minus xt minus 1 or 1 minus this. Point is, if I know xt minus 1, nahi, theek hai, chalo, let's put it this way. So I clearly see that xt minus 1 is dependent on what, xt minus 1. xt minus 1 is nothing but it. It is dependent on what, xt minus 1. Therefore, this process does not have independent increments. Again, it is my increment over here. If you'll see the distribution of it, +1 -1, probability is e to the power minus mod xt minus 1, 1 minus e to the power mod xt minus 1. So clearly my increment is depending on what, xt minus 1, if you will see the definition of independent increments, xt minus 1 should have been independent of all past values including xt minus 1 itself, but that is not the case over here. Therefore the process does not possess independent increments. So you can write it in this way, structured answer. The natural increment for this process is xt minus 1. That is IT. That is IT. Although the values which IT can take, are fixed, but the probabilities are dependent on xt minus 1. Hence, xt, hence the process xt, does not have independent increments. Does not have independent increments. Second part would have been direct. Given it has independent increments, it is therefore Markov. No, ऐसा नहीं, we can't say that. If it is independent increments, it has to be Markov. Even a process which has non-independent increments could be Markov, and we will see in this case only. Now for Markov, what did we say? If I know xt, I should be able to determine xt plus 1. In this case, if I know everything about xt minus 1 and using that, if I can determine xt, then my process should be Markov. Yes, so now here, if I know xt minus 1, I know this thing, I know what value IT takes. IT takes either plus 1 or minus 1, and I know the probabilities as well. So using all this information, I can predict what xt will be. Again, keep in mind when I say predict, I am not saying the exact value. What I'm looking at is the set of possible values along with the set of probabilities. So in this case, clearly, if I know xt minus 1, I am able to estimate xt, and therefore the process is Markov. In the earlier case also, if you take a look at this question, can you comment for this one? Does this process have independent increments or not? So here also yt becomes my natural increment. Yt is nothing but xt minus 1. Yt is always taking fixed values with fixed probabilities. So therefore xt minus 1 does not depend on past only. Therefore this process has independent increments. And directly, if this question would have come, you can say from part 1, you can directly use the result. Now if at all explicitly they ask you in examination, no explain, then you have to explain. If just written, just check whether it's Markov or not, so you can directly use this particular result. And if they ask you to explain, then just give a reason in words why it is possessing Markov property. So this is all we have for chapter 1. Do go back home, take a look at the material, practice the material questions. There is a separate revision notes for this for chapter 1 itself, devoted completely to chapter 1. So do give that a shot as well. Okay. Apart from this, any doubts with respect to topics covered today? Avanti, Sachin, either of you any doubts? If not, let me know in chat box. I'll conclude the class. No doubts then? Fine. We'll wrap it up over here then. Thanks. Bye.